Dear participants, good morning, good afternoon, and good evening to everyone, wherever you might be. It is an honor for me to welcome you to the webinar titled The Role of Hydraulic Modeling in the Design and Safety of Hydraulic Power Plants. This evening, it is a joint initiative between the YPM Venezuela and the YPM Portugal, as an effort to organize from the synergy and collaboration between our two organizations. The idea of this webinar arose from the shared desire of both YPM teams to create a space where experts in hydraulic engineering could share their knowledge and experiences. We firmly believe that hydraulic modeling is essential for the efficient design and operational safety of hydraulic power plants. And our aim is to highlight its importance during this event. We are deeply grateful to our distinguished speakers for being here with us today, and to all of you for your participation. We hope this webinar will not only be informative, but also inspiring, and that it will foster new ideas and collaborations in the future. Without further ado, we start with to introduce the participants, and thank you again to all participants, all the guests to connect and to enjoy the webinar. I will also kindly ask you to leave any questions that might arise during the presentations in the Q&A chat. And I will proceed to read those questions at the end of the presentation of both speakers today. So I will start to introduce Lourenço Mendes. He's an auxiliary research at the National Civil Engineering Laboratory of Portugal. He has been with the Hydro Resource and Hydraulic Structures teams for the past 12 years. His activity is mainly focused on research and consultancy to validate and optimize large hydraulic structures using computational fluid dynamics, mainly the open software. Lourenço graduated in civil engineering at the Institute of Superior Técnico in Lisbon in 2006. It means 18 years ago, so I have a lot of experience. And in 2022, he concluded a PhD focused on the computational fluid dynamics of aerostatic flows in spillways shuttles. And also developed at he did his PhD also at the University of Cambria, or Universidad de Cambria. His presentation is going to be about the integrating physical and CFD models to study large hydraulic structures. So Lourenço, welcome, and it's all yours.
Good afternoon, everyone. I salute you. I hope you enjoy this presentation. I also want to salute all the members of the panel, Ingrid, Professor Arturo, and Emilio, also, and Antonio. Also both the teams of young UPI of Venezuela and Portugal. So I will start my presentation as I need to share my screen first. Please just wait a minute. Okay. Now, can you see the screen with the PowerPoint presentation? No, but not this one. Sorry. I had to change because the one that I want to share is this one. Okay. I just hope this bar goes away. I don't know exactly how to do it. Maybe we'll do it with it. Okay. So this presentation is the title of Integrating Physical and CFD Models to Study Large Hydraulic Structures. And it's the description of the work that we have been developing at LNEC, which is the National Civil Engineering Laboratory of Portugal, that is at Lisbon. And this work was mainly developed by myself, Lourenço, and Antonio, who is also in this session today, and also with Engenheiro Melo and Engenheira Teresa Viseu. So let's begin. The main idea of our activity is to prevent such disasters as the one that you can see in this picture. This was in China. It's like a small bridge with lots of cars because there was a very, very big flood. And this flood happened due to the breaking of a dam, which happens due to the malfunction of some element of the dam. This is another example of the kind of damage and disaster that that can result from dam breaking or collapsing. And also this image is also a bit older one, but it's quite spectacular, let's say. But sadly, it always involves many losses of lives and also of materials and resources. So what do we do? At LNEC, our team is called NRE, and is the Hydraulic Researches and Hydraulic Structures team. Yesterday, Antonio and Silvia also presented our activity, so I'm not going to extend that much. We have 70 years of experience doing research and consultancy, validating and optimizing large hydraulic structures, mainly spillways, but lots more hydraulic structures, also some urban drainage, large hydraulic structures as well. So in the last 70 years, we have been developing mostly our activity using physical modeling to study these large hydraulic structures. I have to mention that we also do some flood analysis and all other kinds of hydraulic researches and hydraulic structures related issues. In the last 10 years, more or less, we started using CFD, computational fluid dynamics, to help us study our problems in integrating it with the physical modeling. And in the future, we hope to be able to integrate it even better with more efficiency, connecting our models, both the physical and the numerical, to also the prototypes, to have more data, to be able to be more accurate, and also to have a faster and response to our challenges that we have from companies, mostly designers, so engineering designers that need help to validate and optimize their solutions, but also large activity on research, as you will see. So just a brief mention, because this was explained better yesterday. In 1951, we started with our physical models. The first one was the dam of Campilhas in Portugal. And our first international model was to Brazil and started the study in 1952. We have lots of national physical models. You can see here some examples of most spillways, as I said before. We analyzed some different elements, like I think you can see my pointer here. Yes, the pointer, laser pointer. You can see here jets, you can see an intake, the shapes of the guidance walls. Here, a traditional way of analyzing it and be able to change it with a sheet of metal, flexible sheet of metal. Also some improvements on this spillway over the concrete dam that we change these shapes. We also study velocities in turbulence and vorticity. This is an outtake of an hydroelectric power plant. We also have some erosion in rivers. This is a bridge pile, but also caused by the jets impingement, and also in erosion in earth-filled dams. So regarding, excuse me. Okay, we also have lots of international studies that we've developed in the last 70 years. Overall, we've studied more than 150 dams, and most of our studies, let's say, are regarding dams and spillways, and 70% are national and 30% are international studies. Okay, in your left bottom corner, you can see a typical size of a physical model that we have. It's more or less between 10 to 20 meters long by 5 to 10 meters wide. We also have some permanent facilities to do research, as you can see, and this was further developed yesterday, so I won't talk about this today, but you can contact us if you have any curiosity on what we have been doing. Yesterday, we also explained that our construction techniques for the physical models is evolving, and we are now using some automated and new materials, more ecological, but also faster to build. And this was also developed by and presented by Antonio yesterday, so you can also talk with us if you have curiosity in this subject, if you didn't have the opportunity to see this yesterday. Okay, so now just to introduce a bit of engineering in this presentation. Now I will use the example of the spillway chutes so that you can see how important these studies are. So spillway chutes are a safety structure of dams. They prevent the overtopping, which is the water passing over the dam, which typically or almost always will lead to the rupture of the dam. And so what we do is design validation to prevent those accidents and those consequences that I showed you in the beginning of the presentation. Typically, the flow is very complex with very high velocities and a lot of complex phenomena like cavitation, also the abrasion or damage of the structure, which is typically concrete. The flow has very high turbulence. It's very, very complex with roll waves, cross waves, and other non-linear phenomena. And one of most challenging aspects is the air entrainment. So typically the flow, when the velocities are high, starts to mix with the water mixes with air. So we're not studying just a water flow, we're studying a mixture, and the phenomena that are involved are very complex. So for instance, you can see here 3 pictures of a spillway. These are actually 2 different spillways in Portugal, and you can see the effect of the air. So where it's white, and also some cross waves in the center bottom picture. And I'm not going to develop this topic much more, but you will see later why this is so important, because mainly when you mix water with air, the flow is as more volume. So the walls of the spillway must be higher, and also you have some other phenomena. But sometimes it also helps because the presence of air, for instance, reduces the cavitation damage, or might reduce. As an example, you can see in this spillway, there are two towers. I can show here two towers where air enters in the bottom. It's like a step where the air is sucked, and the air enters the flow and to prevent cavitation. So in 2010 at LNEC, we started to think about using numerical modeling to help us in our studies. Then we called this integrated modeling, where we use both the physical and the numerical to study the problems more accurately. In a more global way, we can see physical modeling as reliable because it's not calculations, it's not models, it's pure water running in a scaled geometry of the dam. We already have and everyone has, like the scientific community and the engineers have lots of experience regarding the scale effects and that this type of models have, but building them is very time consuming. Also, operating takes a lot of time because it requires a lot of instrumentation, sensors, and also people working, and actually it costs quite a lot of money and takes a lot of time. Some effects are not being able to be reproduced at these scales that we are talking about. Even those large models that I showed before, for instance, air is not being able to be reproduced accurately. On the other hand, we have numerical modeling, which started to be more known and more used in the beginning of this century, 21st century. It's very complex because it involves computational calculations and models and lots of simplifications and lots of different approaches. It's difficult, but because we need data from physical modeling, but even better if we could from prototypes to be able to calibrate and validate the results. But on the other hand, for instance, it's more real, or it can be more real to model air and water, the mixture. It can be more similar to the prototype if it's done properly, and if it's also quite faster and less expensive to operate. But the technology is not completely developed, and also the good practices are not completely established. So I would consider this a technology in development and in terms of research and also engineering. So to explain this, I will give you these are some examples of studies that we done in the beginning. In 2014, we started to do the first studies in numerical modeling. But I will bring you two case studies. The first one is a dam in Albania, the Fierza Dam, and this was done in 2016. We started by 1D numerical modeling to understand the water levels on the river for the different discharges. Then we did CFD modeling, 2 tests to understand better how the system works, using just one spillway, both spillways, because this dam has 2 spillways, to understand better the dynamics and have an idea of how the physical model would function. Using this information, we built the physical model. We did some tests. We done some simple validations of the numerical model, and with the physical modeling, we were able to understand the problems that this dam has with the operation of the spillways, mainly damages on the left bank. And you can see this is the solution that we propose to protect this bank using riprap, which are big rocks or blocks. And you can see on this image the the effects or the expected damage if there was a very large discharge during a long period of time. In the end, we also used again the CFD to understand a bit better the phenomenon. So we did CFD in the end with more resolution, more accurate, to understand better the phenomena that are involved. I hope this is a video, but it's not playing. Let me just try to, I don't know why. Okay, it doesn't matter.
I think if you stop presentation, you can show the video. Sometimes that happens.
Stop sharing? No, stop the
No,
presentation.
stop sharing. Stop in the presentation.
Now I can do it.
It's because of the pointer.
Yeah, now you can see here the example of a physical modeling comparing with the numerical modeling, the streamlines and the velocities that we found. And everything was checked, and this was very useful for us to understand better the problem and to propose better solutions. So in this study, we used a two-phase volume of fluid model, which is quite known in the OpenFOAM software suite called Interfoam, and it was very useful for us. The process was very efficient, but this model doesn't models aeration properly. So it is an advantage, but to use together with physical model at the physical model scale, it was okay for us. It was a big advantage comparing to when we didn't use it before. So the next example is a dam in Portugal, which is the Fratel Dam. You can see this is the dam body, like again in this part. This is a top view, front view, and we had to help the developer of the project to understand how they can lower the channel, the restitution channel. This is the power plant, sorry. And they also want to implement a fishway so that fishes could go up the dam. They have a device more or less in this wall, and they needed to ensure that the fish could go from the river up to this wall over here. So they had a design that was improved several times using first numerical model. I will explain why. Because the domain to study was very, very large. It's 350 meters by 90 meters. And this was a very, very large domain that it wasn't feasible to have a physical model that could reproduce this whole domain accurately. To do so, we had to build like a physical model with 50 meters long, something like that, a gigantic model, and that would be way too more expensive than what is reasonable. So we proposed to do a numerical model of the global domain, and then to do a physical model only of this smaller region here, which was the region where there was a fish passage and the outtakes of the power plant. So first, we did the study of the layout of this secondary channel where there was an extra depth so that the fishes could travel, but also to rest. There were some rest zones as well. And these rest zones geometry and location was improved with numerical model studies that we couldn't do in the physical model because the physical model was just localized in the next to the dam. Then, after having the boundary conditions of levels and the velocities, we did continue the studies with a physical model of this localized zone where we had like a weir, and we studied fish passage, which is this white block that has 4 pools, and also a ramp with some blocks that also allows the fish to go upstream in certain conditions. To study this, we did PIV imagery, where we use frames, we do videos, and then we use the frames, and with a technique we are able to know the velocities on the surface using a tracer. This study was completed with success, but thanks to using both the techniques, otherwise it wouldn't be possible. There are some disadvantages because we don't have much data to validate, but once the dam is built, or this solution, not the dam already exists, but this solution of fish passage and the ramp is built, we can then go there and do some measurements to validate a bit more our numerical models. So this study was finished, but in research terms, let's say, to understand better our models and how it can integrate with each other, we hope to do some more numerical modeling of this localized area in the future. Okay, the time is running, so I'm not going to develop this much more, but we have proposed in the IAHR Congress last month, or this month's methodology, where we propose some steps to integrate physical and numerical modeling. So first we do numerical to understand better, have a global idea of the phenomenon. Then we will do physical modeling, and we start with the first design with the physical modeling, and also to get data to calibrate and validate the numerical models. Then with the numerical models validated and calibrated, we can do several tests in numerical models of different configurations or different geometries or different scenarios. In this way, we reduce the number of scenarios that we study in the physical model, and we also are able to study much more geometries or solutions than we would typically do with the physical model due to time and cost constraints. In the end, we can also do a numerical simulation of high resolution to even understand better the phenomena that are involved. Okay, so now I'll pass the testimony to Antonio. He will explain you a bit he will talk about his research activity that is done during his PhD in the last years. Antonio will share his screen.
I think it's sharing.
Yes, it does.
It did everything fine. Yes, let me talk about 2 examples of the numerical simulations I performed during my PhD. First is a simulation of a water jet in his travel to the air, and the comparison of the 2 open foam solvers, interfoam, like Lourenço said, another type of multi-phase solver, a 2-phase Euler foam, which basically is an Euler foam instead of interfoam, who is a Wolf solver. In this case, we don't have this data. We don't perform experimental tests, but we have data from other authors, and I reproduce the exact same flow conditions. It is possible to see here, in order to compare the simulations with compare and validate the simulations with the other authors. A briefly explanation of the results. Looking for the velocities profiles along the trajectory of the jet. Here is the initial section of the jet in the air, and here is the final section of which the referred authors perform measurements. It's possible to see in red the Wolf solver interfoam, and in green the 2-phase Euler foam and Euler solver. In the middle or in the core of the jet, the velocities are more or less the same, but in the lower and the upper nap of the jet, in the more dispersed zone, the two solvers start to diverge a little bit, with the green one, the two-phase dollar foam, matching better the experimental results when compared with the Evolve solver. This is an area of high air water mixture, and due to that, the Evolve solver can have some problems regarding about mesh size and things like that. We do not have time to discuss it yet. Also, I am performing some experimental tests in an experimental facility here at LNEC. Is a 4 meters in this direction and 2.3 meters in the other direction. We are able to simulate water jets from 5 meters per second to 80 meters per second, and pool depths of 0.3 to 0.9 meters, and also submerged jets. We obtain numerical results for the same type of structure with the same dimensions as it is shown in the left figure, and we also make the comparison of the two solvers. We define this type of domain present here exactly with the same dimensions and the same characteristics of the experimental facility. And regarding the mean dynamic pressures at the jet central line, what we found is the other solver, the two-phase Euler solver, performs better, match better with the experimental results, and finds mesh dependency. Here is not possible to see. I'm sorry. Here is the resolution of the mesh, 6 cells in the jack diameter, up to 36 cells, and the Evolve solver never reach mesh independency, what is not a good idea when we are performing numerical simulations. A good practice is to have results independent of the mesh resolution, and the other solver performs better comparing with the experimental data we obtain in the experimental facility and reach mesh dependency. Regarding the air concentrations, the main differences are in the general behavior of the jets. Here in the bottom figures, the Evolve solver also only have for the mesh with 24 cells in the jet diameter. This is a 70 million total number of cells. It's a huge mesh for an experimental facility, and we see only air concentration around the jet, and the jet core at the jet central line has no dissipation along the passage through to the plunging pool. On the other hand, with the two-phase Euler foam, we see some not so clear the air pockets because of the type of the solver, but an air mixture in all of this area, and the core of the jet is dissipating along the traveling inside the plunging pool, as was expected and as was described in the literature. Now back to Lourenço.
So, okay, so the time is running out, so I have to be faster. I didn't explain, but I want to say it now, that our research activity has been mainly on understanding better the numerical tools, in this case the solvers. So we study a lot the volume of fluid, the two-phase volume of fluid, and also the complete Euler solver. During my thesis, I also implemented the subgrid bubble model in the open foam so that we can use it together with the volume of fluid solver. But we had some good results in a spillway chute, but not so good in the impinging jet because it's way more complex. But we can talk to this another day. I also did some comparison of performance in a spillway aerator, where I studied different turbulence models, both the models that I said before, and in different resolutions, so that we can see what Antonio also said before, that when there's an aeration, the volume of fluid is also always misleading, unless that we have a mesh resolution up to the bubble size scale, which is impossible in engineering studies. So the complete two-phase oiler has shown an interesting and very important performance, though it's a bit more difficult and more demanding and also more time consuming than the volume of fluid. Okay, so to sum up our presentation in terms of research, we now have analyzed and we have defined which model that we use in each type of region of in this case of a spillway, but it can be an hydraulic structure. So we would use the volume of fluid in the intake or in the restitution where there is no significant air entrainment, or even in the beginning of a spillway. During a spillway with low air concentrations, we can use the volume of fluid together with a subgrid bubble model. But when there's high air concentrations, typically in steep chutes or aerators or dissipation basins, we have to use a complete two-phase oiler solver or model. Okay, this is our last slide. So in the future, what we want to do, we want to be more efficient. We need more experience. We have done some studies integrating both these tools. As you can see here, one study more of two of them in Portugal. But we need to gain more experience to understand better how models work. So far, there isn't a numerical model that can study erosion properly, and this is also being developed in the thesis of Antonio, especially dedicated to fractured rock beds. And we want to apply the two-phase oiler to large hydraulic structures, which we haven't done yet. And we also would like to develop some research in CFD classification, like having grades like A plus, B, C, D, to better classify the type of numerical modeling, if it's an high quality or an average quality or a low quality. But all these grades or rates are important because sometimes we have to be fast, sometimes we have a lot of time, as in research. So these classifications are important for us. Integrating artificial intelligence also is important, and we would also like to implement some digital twins technologies where we can integrate the prototype, the physical model, and the numerical model in a single digital twin. So thank you very much for your presentation. This is just a small, let's say, it's a didactic simulation that I did for the IAHR Congress that we are in at LNEC last week. It was the European Congress, and as you can see, CFD can also be used to do some images, colorful images, that can also help us to communicate better with the engineers, and also with the politicians or other stakeholders involved in the projects. So thank you very much. Gracias. Obrigado. I'm sorry for the extra time.
Okay, thank you very much, Antonio and Lourenço. Very good presentation. Incredible the amount of experiments that you have been working with. We will have questions for you at the end of this webinar. I will then proceed to introduce the next speaker, Emilio Martínez. Emilio Martínez is an experienced civil engineer with a bachelor degree in civil engineering and a master graduate study program at Iowa Institute of Hydraulic Research. You can correct me later, Emilio. Of University of Iowa, and over 30 years of experience in the hydraulic projects components such as dams, spillways, bottom outlets, powerhouses, and more. Martínez has also participated directly in development of water resources projects across the entire project life cycle, from initial planning, basic design, construction, commissioning, and commercial operation. With the CVG EDELCA, which is the Cooperación Venezolana de Guyana, or Venezuelan Cooperation of Guyana. The background in civil works allow him to create and review operations and maintenance manuals that ensure the continuity of projects, functions, and prioritize safety. In addition, Martínez has knowledge and experience through interaction with international specialists and consulting engineers. He has conducted capacity buildings and training programs for dams personnel. Martínez has also published about 20 technical papers, and he has been co-editor of the proceeding of the 26th International Symposium of Hydraulic Structure entitled Recent Development of Hydraulic Structures, from Hybrid Modeling to Operation and Repairs, with the aim of sharing knowledge and best practices among experts in the field, including operation and maintenance. Emilio, you can start now with your presentation.
Thank you so much. It's the Iowa University of Iowa, Institute of Hydraulic Research, CVG, Corporación Venezolana de Guayana en Venezuela, ¿no? I will share the presentation. A moment, please. Okay, can you see it?
Yes.
Perfect. Okay. Okay, you see it?
Yeah, now.
Okay.
Good.
Okay, let's start. Good afternoon. Thanks for coming in the webinar. Thanks to Young Professional Network, YPN, of International Association of Hydraulic Research, IHRR. I will give you a brief of contribution on hydraulic modeling to the dam safety program of the Caroni River hydropower system between 2000 and 2010 from the hydraulic point of view. The purpose of the presentation is how was applied experiment systematically a dam safety program using hydraulic modeling in a complex system as Caroni River. The content, you will see the Caroni River Basin, development of the hydropower, a background about EDELCA and some achievements, then hydraulic department, why implementing dam safety program, how did it, hydraulic used tools for that, format studies before 2000s, the dam safety program achievements, some remarks and reference. The Caroni River Basin is in the source of America and also a source of Venezuela. The basin has an area of 93,000 square kilometers, almost 960 kilometer length. The average discharge is about 5,000 cubic meters per second. The total drop is 912 meters and high discharge rate of 53 liters per second per square kilometers. In the plan view, you will see the four large hydropower dams on the Caroni River, starting upstream from Guri, Tocoma, Carhuachi, and Macagua. And you will see the river exit to the Orinoco River. Is surrounded by Ciudad Guayana, located in both Caroni River bands. In the longitudinal cross-section, you will see the cascade system where Guri Dam control a reservoir, and the future water from the Guri goes downstream, and the other dams will almost constant head turbine the same water discharge. The water levels in the last 10 kilometers downstream from Guri has a strong backwater effect from Orinoco River. You see all the normal water level is done. Some of them will increase the water level to convey the PMF, probably maximum flow. From Guri discharge, as you will see as follows. You will see here the maximum discharge for the speedwell, Guri 28,800 cubic meters per second. The maximum water level is 270 watt, 1.6 meter above sea level. Tocoma 28, the same speedwell maximum discharge from Guri, and the maximum water level 126.5 meter. Carhuachi 92.5 meter. Maximum discharge for the speedwell 30,000 cubic meters per second. And Macagua, the same discharge with the normal water operation 54.5 meters above seawater level. Setting on CDG EDELCA. In the mid-20th century, Venezuela needs energy because of growing population, petroleum, and important mineral resources at the south of Venezuela. The first study of the hydropower potential started in 1943. The fifth powerhouse, in order to supply energy to use for mineral transformation of the south of Venezuela, needed energy also for the city, and start commissioning in 1961 the Macagua powerhouse with 370 megawatts. Because EDELCA, the Venezuela needed to continue with it to supply the energy demand, EDELCA was born in 1963. Some important achievements that EDELCA did: the construction of the Guri Phase 1. The company acquired the know-how, create also a strong organization, introduced itself into the electricity market as main generator and energy transmission. Also, water resource development for hydropower water was important, and each project need to pass all the feasibility studies. And then the company established its own engineering units in order to get high standard for the construction, and the hydraulic department began operation in 1977. You will see now the facilities of this hydraulic laboratory, who was located in Macagua, in the surrounding area of the Guayana City. The area available for 3D physical models is almost 4,300 square meters for variable head between 1 to 4 meters. It's a huge discharge, almost 5 cubic meters per second, was available driving for gravity, and also the total area for the hydraulic department was almost 28,000 square meters. Well, here you will see the organization on the lab. Ahead of the hydraulic department was a civil hydraulic engineer, administrative assistant, secretary, international consultants, Venezuela consultants, 6 civil hydraulic engineer staff, interns from Venezuela and abroad, instrumentation and data acquisition, engineering support and documentation rooms, short survey and survey team. Why EDELCA implement a data safety program? In 2002, began to come the last project. You will see in this table how projects that were doing in parallel form, according to the master plan. Therefore, the company need to continue it operation and maintenance rules, maintaining the hydraulic system, ongoing globally advanced safety issues and concern about climate change. And also there are available some dam breach studies required by Inter-American Bank. There are also many instruments for dam monitoring and surveillance installed, capable engineering units with experience to continue to establish operation and maintaining rules, especially in civil works. And EDELCA need to continue it with the dam quality governance during final operation of the old system. How EDELCA did it? Well, in 2000, many engineering units implement programs. The IHRR symposium held in Guayana City in 2006 allowed relation with consultants for initiate the program systematically start relation with University Politécnica de Valencia, España. You will see the program until 2010 and at that time with the contract assignment finished, and then you will see here all activities that we did at that time, basic activity for risk management, development, risk management, monitoring, dam safety, operation, communication, monitoring, surveillance, maintenance preventive, maintenance corrective. So we have to continue with these kinds of important program. One of the tools used to evaluate hydraulic structure response to hydraulic event was a 1D numerical model, as you see in the scheme, that Guri, from Guri to Macagua River. The model was set in 100 kilometers of the river length, water profile calibrated and validated. There were 49 gauge stations, 180 river cross section, survey map scale 1 to 10,000 include both river bank. And mannings come from calibration and validation. And the program that we used was FQ, harass, and Dambrae. Also, we have to include for overtopping discharge for each dam, for spillway discharge, curve for area capacity curves, hydrograph from normal river flow and stream flow from 230 years to PMF. Also, we use the available information from hydraulic physical models. Maximum spillway discharge from the PMF entrance to Guri Dam is 48,000 cubic meters per second. We use all the information for energy dissipation tests, hydraulic structural behavior, spillway chute erosion. Here, some examples for scour and erosion tests in Karawachi and Tacoma model scale 180. Previous analysis before 2000s So when review studies in this problem, we have a study for the from the Caroni report. We were thinking about dam safety, a consequence of the breach of the Caroni project. The result regarding the cascade system and its impact of Guayana City was shared with the Guayana City Council in 2007. You will see the inundation map and the right side. Also, this previous analysis before 2000 was avoiding any possibility of the overtopping in Tacoma Dam. You will see that they are close, that you are seeing in the slide. They are so close, almost 18 kilometers. The normal water level is 126 meters above sea level. The reservoir volume until 127.50 meters above sea level is for PMF. The two spillways should be open at the same time. As you see in the plot on the right side, the discharge in a cross section close to the dam, the discharge comes from 5,000 cubic meters per second to 50,000 cubic meters per second. And the Tacoma water reservoir level only dropped 10 centimeters. We are confident and we are very sure that this dam should be open the gate at the same time in order to avoid overtopping, even though the dam has enough freeboard. We seen about protect and aging structure like a transmission tower. Number 5 here in the picture. This transmission tower conduct energy from powerhouse Guri to the switch yard. The tower was built in the 20s and at that time has more than 20 years of service. At that time, raw foundation present weak performance due to discharge from the spillway. The company decided to protect the tower with a concrete wall surrounding the tower. And here the test in the hydraulic modeling. But this analysis shows us that dance structure could be aging when it's operation, and they will need maintenance. So there are many things that we did in the program between 2000 and 2010, and then I will highlight some of them. For example, the establishment of the Dam Safety Committee, Tacoma Dam Bridge Study request by the Inter-American Development Bank, new emergency action plan for Tacoma Dam, and also we practice or we did drills. The program was implemented also a training period. And also we did risk analysis for Macagua Dam, also new inundation map for all the river, especially for the last 10 kilometers of the Caroni River close to the Guayana City. And here some example of the HERRAT calculation. Also, in that period, we did the manual for the spillway operation rules for the cascade system. We set an area of the reservoir and mandatory sums in the reservoir to release water in order to protect the dams. Also, Caravaggio Dam reservoir filling. Durante the Caravaggio Dam reservoir filling, we implement an emergency action plan. Also, in that period, we did a formal inspection in Macagua Dam, done by EDELCA engineers, reviewed by international professionals. Hydraulic failure modes that we studied were overtopping, spillway scour erosion, pipe flow, new hydraulic evaluation. Also, we did it in that period for the Caroni River basin. Also, we did a formal inspection for the Guri Dam by EDELCA engineer. The failure mode that we studied were overtopping, spillway scour erosion, spillway cavitation, and shear force erosion. You will see in an example when geology and hydraulics engineer in the photo are evaluating spillway scour erosion. We were looking for rod joint set orientation and did also using Annandale methods to determine the rod resistance and also the power to the jet stream from Guri spillway, and also all design criteria in Guri for energy dissipation. Finally, should spillway erosion. Aeration, we check the aeration system fulfill all the design criteria for that time, but because the shear force from high water velocity of the spillway, almost more than 20 meters per second, and some reaction between the water quality and the surface concrete produce these kinds of problems that you see in the chute one in the spillway, this hole here, because the concrete, the surface concrete, this degrade all the water degrade all the material of the concrete surface. And then we repair the spillway with a better concrete mixing and good bond strength between new and old concrete surface. Thanks to the concrete laboratory, monitoring surveillance team, and structural team, obscure hydraulic units, and other important engineer units and former EDELCA professionals. The final remark for that is, as the finish of dam projects, we high engineering level, operation and maintenance and dam safety program require the same high quality of dam governance. Combine field data, calibration, validation, alternative access, numerical model, physical model, and data behavior from real hydraulic structure when all of this information is available, ensure reliable results. After a dam begin operation, hydraulic engineers with other important engineer areas, including hydrologists, need to be in the dam operation and maintenance of the dam. Here are some references that you can use in order to investigate more about this step. Many information is classified for the company, the actual company, and you will see this reference. And thank you so much for your attention, all of you.
Excellent. Thank you very much, Emilio, for your great presentation. Very good images to get an idea of what you were explaining about. And so I will now proceed to read some of the questions from the chat. The questions there are some questions that both speakers or also Antonio could help to answer. So I will read the question and you feel free to take the word to answer. The first question is from Dr. Dust and assistant professor for the National Institute of Technology of Patna in India. And he asked, K epsilon or K omega, which one is better if we go with BOF approach? Less turbulence model can we use for jet scenario? Maybe it's more for Lourenço.
Maybe we can answer both. I will regard the first one, and Antonio will answer the second one. So in terms of hydraulic structures, large hydraulic structures, from our experience, because this has a lot to do with the type of structure, but also the number of cells, or I mean the resolution that you have available. For us, I would suggest the realizable K epsilon or the K omega SST. We had some very similar results with both these models, but please keep in mind that the normal or the typical K epsilon is not so good compared to these ones. I'm also writing the question so that if someone wants to answer it. Regarding the second question, just Antonio will answer it, but in large hydraulic structures is, I would say, almost impossible in typical studies, unless it's like a very advanced scientific research to use the LES turbulence model, because the time and space resolution to study hydraulic structures needed to apply this turbulence model would be huge. So it's almost impossible to computate it in a useful time. In terms of I would say scientific applications of facilities, Antonio has more experience, so he will answer it.
Yes, in my case, in my particular case, I make some tests and some calculations if less is possible or not to apply. I do not have enough mesh resolution to study LES, and in my case, my objective is to study the pressures at the boundary. Due to that, LES has to have a huge resolution near the boundary also. If you are studying a jet in the air, maybe the mesh resolution will be not a critical path, but in the it will be time consuming to perform the simulations. In my case, I mixed LES and K omega SST model, a RANS one, and I used the detached eddy simulation to make some tests. It gave me some results, some good ones in terms of mean pressures, and I am able to simulate pressure fluctuations at the bottom. On the other hand, one simulation, the simulation takes 4 times more to perform let's say 1 second of simulation in a normal model takes, I perform 2 seconds in 1 day, and with detached eddy simulation I only have possibility to simulate in 4 days 1 second, and it's very time consuming, and in some cases it's not possible to achieve a result during the schedule we have. But in the future, I think LES will be more and more a possibility, since the computational cost is decreasing and the computational power is increasing all over the world.
Okay, very good. Thank you, Antonio. I have a question for Emilio. The question is, what % of Venezuela's electricity demand is met by EDELCA, and how has this changed over time? what are other important generation assets in the country?
Okay, thank you for the question. I don't have actual information for the system, but in that time, the Venezuela matrix system supply is 60% hydropowers and 40% fossil energy. So for other important generation assets in the country, in the south of Venezuela, we have probably 9,000 megawatt available to develop. Also, we have gas also for generation. Also, there are in the coast of Venezuela, there is a potential for wind energy for generate electricity. And also we have the sun energy, but in order to apply this renewable energy, not traditional renewable energy, I think we have to get more technology to handle those energy. But at the end, in my conclusion, we have to continue with the 60% or more of hydropower and the net for gas.
The net for gas, hydropower and gas are the main sources. Okay, so there is another question in the chat. I want kindly remind to the participants to write your question in the chat. But I have a question also for Emilio. During the presentation, you mentioned that in the cascade system in Caroni River, you mentioned that if you open the gates for Guri, is also we open the gates for Tacoma.
Yeah.
Also, what's at the same time? Yeah. And but what happened
Yeah.
with the other hydropowers downstream, those two, like Karawachi and Makawa?
Well, there is enough travel time of the way, so
Okay.
there is enough time. So, but Tacoma is so close. So the reach between Tacoma and Guri, there is a canyon there between Tacoma, Guri. These are in a canyon, and the water and the velocity are very quick. So, and then the entrance of the reservoir of the Tacoma, there are many islands. The reservoir is too wide, so close to the Tacoma Dam. So the response is almost immediately. The way from the Guri Reservoir, the discharge from the Guri Reservoir, almost you can feel it in Tacoma about in less than 15 minutes. The way. So it's better in order to avoid any possibility thinking about dam safety, and also when the dam all the system is stay operated, it's important to open the gates. We recommend open the gate at the same time to avoid any problem, in order to increase the water level in the reservoir, even though we have enough freeboard.
Okay, great, thank you. Good. And I also have a question for Lourenço or Antonio about the physical model. Just for curiosity, once you create or build up your physical model, about how many experiments can you run in the same setup without considering that you will introduce sort of damage or is overuse or is, so to say, it's not a long-lasting model. It's just for temporal use. So around how many experiments do you think it's possible to run?
In our case, depends on the tests. We try to have our physical models as long as we have space in our facilities, and we perform the tests, and with our knowledge, we do not have too many type of failures, let's say, in the materials during the tests. If we have, we can fix it. We try to fix it, but it's not a normal case to have material or material damages in the physical models. If we make some changes in the physical models, the last solution can maybe not possible to go back to reproduce the first solution if we have to cut some parts or things like that. With the new the new technologies, we are making models easier to make changes and easy to go back and forward almost in real time with 3D printing. And at this time, we are not facing any type of problems with the materials during the tests. Sometimes it occurs because of changes of temperature in the facilities, but we can, with our long experience, we can deal with that normally. But every day is a challenge in the laboratory.
I believe so, yeah. Okay, and a question from Emilio. When you were talking about the dam breach study that was done in 2000, if I understood correctly.
We did two dam breach studies. Before 2000, and then between 2000 and 2010.
Okay, and those studies, especially probably the last one, does that consider all these new concepts and studies about climate change and yeah, you know, all these.
Okay, well, the climate change is everybody's worried. Well, it's an interesting matter right now because in my opinion, hydrology events are more frequently, the duration is more is long. You have to act very quickly. So for those studies, I think we had enough capacity with the hydrograph that we use it, as you see in the presentation. But I think it's time to have a new hydraulic evaluation for the climate change.
Okay.
You have to evaluate constantly.
Okay, that could be a new evaluation coming out maybe in the future.
Yeah.
How often are those evaluations? Regularly?
Well, for that time, we almost 20 years in between. In between, yes, 20 years, 10 years in between.
Okay, thank you very much. We have another question from the participants. It says, when building dam breach models, estimating where the bridge starts and high progress over time is challenging and has large uncertainty. Can physical models be used to gain further insights about this? I noticed most of dam breach models from EDELCA are 1D. Would you expect significant difference if it is updated using a 2D model?
Well, probably not much because probably not much, but now right now the HRAF, for example, have a 2D dimensional capabilities. So the HRAFs are improving more. But one thing about the Caroni River is that conveys a lot of convey water in the center of the channel. He has a big cross section, I think, big cross section, wide cross section, and rapid flows. So probably don't change too much, but of course we have to do the study with the capabilities.
Okay. And I also have one more question for any of you who have had experience maybe with the physical experiment. And I saw that and the spillways is also we saw in the presentation from Emilio, could be common. It's common to have this like a, I don't know how it's called, but it's like an erosion of the concrete surface due to the water or the interaction with the water. So, like for example, in 2017, I see there was this incident in US in the spillway of the dam. I don't recall the name, Orovila. I could maybe find a picture later, but it can happen that the surface concrete sort of deteriorate over time due to the friction or with the water. Do you have any experience experiment model with that? Have you or physical model? Sorry, with that.
Well, in our case, we don't have this experimental experience, but when the concrete laboratory was designed, the mid they did experiment in put the they were more worried about the chemical, the water quality of the Caroni River affect the mixing of the concrete who was there. They put some tests in the hydraulic lab and was there for 1 month or something like this, and it's worked perfect. But we didn't experimentation about the time friction force. Okay. I don't know what the others panelists.
Yeah. Antonio, Lorenzo, had experience with it?
No, not too much, because in physical models at the scales we are using, these type of phenomena are difficult to be present, and maybe with larger physical models but it is difficult because the size of the scale effects of these type of things, and we are not scaling the materials in the physical models. We only make a similarity by fluid, and water is water, concrete is concrete in the physical model, but the velocities are not the same, and maybe some scale effects will affect that.
Yeah, absolutely. Yeah, and finally, I think one last question is about for example, in the presentation from Emilio, you just mentioned that there were some studies about erosion, piping erosion in those airfield dams as part of your general study. Mm-hmm. And also Lorenzo mentioned in his presentation that there has been some, or like among the future work, also to do some experiments about erosion in dams. Have you, and Emilio, you mentioned piping in airfield dams, but have you also do studies or safety assessment about potential contact erosion in those areas where the airfield dams is in contact with concrete structures, the spillways or any other structure?
You mean in abutment contact with the abutment of the dams between
Embankments,
structures?
yeah. When the embankment
Oh.
dams is in contact with any
Okay, well,
consider contact erosion.
we were very close to the monitoring and surveillance team to investigate them, and they analyze all this instrumentation. At that time, they didn't find any problem of that kind of shit, but for the dam break studies that we did, we immediately apply what happened with the bridge when there is a pipe flow in the air dams. So we apply and we seen the consequence and compare the two of overtopping and pipe flow, and then we the effect of the major consequence of the overtopping are bigger than the pipe flow, but for the risk analysis or for the formal inspection, the surveillance team, instrumentation team, and also the panel review, they didn't find any problem in the abutments. Okay. Yes, but we did calculation.
Okay. Yeah, well, I think our time for questions is coming to the end. I don't see any further question from the audience, so I will proceed to conclude the webinar today. Thank you very much to Lourenço, to Antonio, to Emilio, and also to all the speakers from yesterday, as well as the team that was organizing the event, Elsa, Dayana, and other members. Thank you very much for arranging this event. Hope it's the first of many collaborations. And as you see, it's very always interesting to know, and especially in this kind of webinar was very interesting to see the combination between model, numerical model, physical model, and real cases. So thank you very much for this opportunity. Thank you very much for all those who took the time to participate and attend the webinar. So
Bye-bye. Thank you.
Bye. Thank you.
Thank you very much.
Thank you so much.
Bye-bye.
Bye.
Thank you. Bye.